Woohoo! Welcome back. Today we're going to be talking about another little snack of upper and lower bounds theorem. And here I'm going to point out that there are a lot of theorems in math. A lot. And some of them are really useful. Some of them are really useful and you hardly ever use them. Some aren't very useful, but when you need them, you need them. And a lot of them are somewhat hard to understand. And unfortunately, this one is another one that's going to fall into that category of theorems that are hard to understand sometimes for some folks, and also possibly hard to remember. And so when we run across a theorem like this, as you might have noticed in your time in math classes, we don't tell you about all of them. We don't even name all of them. Sometimes we just say, hey, look, this thing is true. And so in this case, we're doing two things. One, we're starting to introduce you to the structure of mathematics, which is that there are a lot of things which we have gone, a lot of tools which someone has gone to great pains to prove, to make sure they are true, and then they are effectively facts that we can use as tools to help us solve other problems. So we're introducing you to the structure, but we're also going through a couple of these to give practice, because some of these where it's another one which when we read through it, you're going to say, huh, look at that. Isn't that a thing? But it's good to start practicing because this is the structure of math. And the good news is this problem, a lot like the previous video with Descartes' rule of signs, this is actually easier in practice. So we're going to do a practice problem. And then in the next video, as I told you, we're going to do one polynomial and just go through all the rules so you can see how they all fit together and how we can use the rules to help us save us time. So they're actually worthwhile. And even though I totally squashed Sharktopus in the last couple of videos, he has agreed to join us again because he is smooth and continuous. And so let's get started. So the upper and lower bounds theorem. Let P be a polynomial with real coefficients. Again, this is important. The instructions are important in math. If we divide P of x by x minus b, now we use a and b here, and I know this could be a little bit jarring because we were using c before, but the thing is a and b are used as upper and lower bounds, and so they want to use letters other than c so we could have two different ones for the two different parts. So it's just a little different. So if x minus b and b is positive, so this is a positive possible zero, using synthetic division, and if the row that contains the quotient, so the bottom row, and remainder, whether it's 0 or not, has no negative entries, then b is an upper bound for the real zeros of p. So far, so good? If we divide P of x by x minus a, with a being negative using synthetic division, and the row that contains the quotient and the remainder, okay, and again, the remainder does not have to be 0, then if they're alternately non-positive and non-negative. Now notice this is a little different than the rule of signs. Non-positive means it could be 0 or negative, and non-negative means it could be 0 or positive. Then a lower bound then a is a lower bound for the real zeros. So again, it's perfectly acceptable to burst out into hysterical laughter at this, especially if you're working on your midterms right now. So what the heck is going on? Let's take a look at an actual example. What does it look like? So if we've got P of x, right, and here's our polynomial, x to the fourth minus 3x squared plus 2x minus 5. And we're supposed to show that all the real zeros lie between -3 and 2. So those are our two numbers to test. So I'm going to start with 2, and I'm going to use synthetic division. So I'm going to have to convert this into the synthetic division coefficients. So I've got 1. Be careful here. 0, you got it. -3, because there's no x cubed. 2 and -5. Okay. So 1 comes down. 1 times 2 is 2. 0 plus 2, 2. 2 times 2 is 4. -3 plus 4 is 1. 1 times 2 is 2. 2 plus 2 is 4. 4 times 2 is 8. -5 plus 8 is 3. Okay, so 2 is positive. That's important. So we're up here in number 1. So 2 is positive, and all of these, the bottom line, there's no negatives. Then 2 is an upper bound. What is an upper bound? An upper bound means that's the biggest one. So that means that if you were going to check 3, do you even have to bother checking 3? And the answer is no. 3 is not going to work because 2 was the biggest possible. And in fact, 2 doesn't even work. So nothing bigger than 2 or 2 will work. So all those possibilities, if you had to check 10 or 100 or 1,000,000, you're done. Okay, now let's try -3. Now -3 is negative. I know that sounds silly, but I just want to emphasize that. That's negative. So 1, 0, -3, 2, -5. Let's look at what this looks like with synthetic division. I get 1 times -3, -3, 0 plus -3, -3. -3 times -3 is 9. -3 plus 9 is 6. 6 times -3 is -18. 2 plus -18 is -16. -16 times -3 is 48. 48 plus -5 is 43. Now let's take a look at these. This is negative land, so we're in number 2. So if we divide using synthetic division, and if the row that contains the quotient remainder has entries that are alternately non-positive and non-negative. So our entries went non-negative, non-positive, non-negative, non-positive, non-negative. So they're alternating. Now, why don't we say positive and negative? Well, the answer is you can have zeros in there. So this one would allow zeros. This one's, it's really easy to see. Bam to bam bam. So this is alternating. So that means -3 is a lower bound. So now, what does this tell you? You only have to check numbers between -3 and 2. So if you have a whole lot of numbers to try, and sometimes you'll end up with like 20 different possibilities. If you can eliminate all but the ones that sit between a very small band of numbers, it cuts down the work you have to do. So that's why we teach this, this will be useful if you're trying to find zeros. Okay, so let's try another example. It says, show that all the real zeros of p of x, which is equal to x to the 4th plus 4x cubed plus 3x squared plus 7x minus 5, are greater than or equal to -4. So we want to show that -4 is a lower bound, right? If we want everything is greater than that, we want to find a lower bound. Okay, so we synthetic division. 4 goes in. What are my coefficients? I've got 1, 4, 3, 7, -5. Do I have all of them? 0, 1, 2, 3, 4. Yes. Okay. So 1 times -4 is -4. That gives me 0. 0 times -4 is 0. That's 3. 3 times -4 is -12. -5. -5 times -4 is 20. 15. Now, at this point, people get very nervous because they're like, wait, these alternate, but what about this one? This one's 0. This counts. So it goes from positive to non-positive. Oh, I don't know that that helps. Let me not write it that way. Non-positive. positive to positive to negative to positive. So a 0 counts basically is whatever you need it to be. In this rule, just this rule, zeros are like wild cards. They count however you need them to count. So 1, 0, 3, negative 5, 15. That counts as alternating. So negative 4 is a lower bound. By the way, is it a 0? And the answer is no. It is not a 0. We end up with a remainder of 15. So they're all greater than or equal to negative 4. We know that they're all actually greater than negative 4. So that's it. Woohoo! That's your snack. So enjoy this little snack. Again, the next video, I know it's very exciting. Are you ready? Sharktopus is very excited. I'm very excited. In the next video, we're going to attack a real live, and humanely. We're going to humanely approach gently a polynomial and go through all of the rules that we've got to kind of show how do they all work together. And then we're going to find all the zeros. Yay! This is very exciting. So definitely take a break, get some hydration, get a snack, you know, get your eyes on something green, and then come on back because it's going to be very, very, very exciting. And I will see you very, very soon. Woohoo! Math on.